Hi, this is Alfawzia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in today's video is segment of a circle and its area. First, let's see what is the segment of a circle. Segment of a circle is nothing but a region bounded by the chord and a corresponding arc. Lying between the chord's endpoint is known as segment of a circle. In this figure, this region is called the segment of a circle. It is to be noted that the segments do not contain the center point. The segment of a circle divides it into two regions, namely major segment and minor segment. The segment having larger area is known as major segment, and the segment that just has the smaller area will be known as minor segment. So in this figure, this region is called minor segment and this entire region is called major segment. So in order to calculate the area of a segment of a circle, we should know how to calculate the area of the sector of a circle. Okay. Imagine a pizza. The pizza slice will be called a sector, and which is cut from the circle by a chord will be called a segment. Okay. This is the difference between a sector and a segment. So what are the common sectors that we come across? The quadrant and a semicircle are the two special types of sector. We know that semicircle is nothing but half a circle. Quadrant is nothing but quarter of a circle. Let AB be the chord. Center of the circle is O. Let this angle be theta, and obviously these two will be the radius. ABC would be the minor sector, and this would be minor segment, and this would be the major one. AOB equal to theta. We calculate this theta in degrees. Then the area of a sector AOBC will be given by the formula. Let me write the formula for you. So this is the formula for the sector, this region. And let the area of the triangle AOB be, I'm denoting this by A, but by a suffix I'm going to write as triangle AOB. For this one, we are just going to use the area of a triangle formula. So the area of the segment ABC will be given by area of the sector, this one, minus this one. So I'm just calculating this piece of pizza and subtracting the entire one and the smaller one. Just plug in these values. Now let's calculate the area of the triangle AOB. Calculate the height of AOB, that is AP, using Pythagoras theorem. I have drawn an altitude because we need height in the triangle area. So I have just drawn, and the point of intersection will be P, and it meets the chord AB at 90 degrees. So we'll be using the area of the sector AOBC. When we get a right triangle, we can easily use Pythagoras theorem. So AP would be equal to square root of differences between the squares of the other two sides, half of AB. So doing algebraically, we can calculate the value for AB. Though we don't know the exact value for R and AB, we can just create a formula for that one. Just subtracting 1 by 2 AB the whole square from both the sides and swapping the sides, we get this. We need to find the value for AP, so I'm just taking square root on both the sides. In case if the value for the AB, the length of AB is given, AP would be equal to, so the area of any triangle would be equal to half times base times height. Base is AB and height is AP here. AB, AP. So by substituting these values in area of the segment formula, we can easily calculate the area. There are two important theorems on the segment of a circle. Once we learn those two theorems, it will be easier for you to calculate the area, because we will be applying those theorems while calculating the area of a segment. Here is the statement of the theorem, alternate segment. The alternate angle is the angle made in the other sector from a chord. Here we are going to prove that the angle AOC is nothing but twice the angle ABC. Okay, let us prove it. I have just named all the possible angles here. Okay, consider the alternate angle ACD as X. This is equal to the angle ABC shown on the other side of the chord, where DC is a tangent to the circle. The triangle ABC has points A, B, C on the circumference of a circle with center O, and join the points OA and OC to form a triangle. I have joined it. Do you see the line in red color? This forms a triangle AOC. Let angle ACD will be equal to X, and same way OCA would be angle Y. We all know that tangent to a circle is at right angle to the radius of the circle. Am I right? So if you measure this angle, you'll be getting 90 degree. If you add X and Y, you'll be getting 90 degree because tangent is right to the radius. Let this be equation number 1. I have bisected the triangle AOC from the point O. Then the triangle formed is a right triangle. Let this point be E. So when you divide any triangle into two equal halves in this place from these one of the vertices, you can easily find two triangles which has 90 degrees, a right triangle. Am I right? So let the bisected angle be Z here. I have mentioned these two angles as Z. So AOE will be equal to COE because the angle is bisected here. Angle bisecting means the angle will be divided into two equal halves. So AOC is being divided into two equal halves, Z and Z. We know one important concept. Sum of all the three angles of any triangle would be equal to 180 degrees. Am I right? So let's apply this fact in the triangle COE. So what are the three angles within the triangle COE? Z, Y and 190 degree. Subtract 90 degrees from both these sides. So you will get one equation with Y plus Z. 180 minus 90 is 90. Let this be equation number 2. So equating equation 1 and 2, we will get, I'm equating equation number 1 and 2 because right hand side of both the equations is 90 degrees. So I can equate the left hand sides of the equation. We can just cancel out the common factor. I mean, if you subtract Y from both these sides, you'll be getting X is equal to Z. And from the figure, we can know that angle ABC will be equal to ACD, which is nothing but angle X. Therefore, angle AOC will be equal to 2Z. We know that X is equal to Z, so AOC will be 2 times X. X is equal to angle ABC. Hence the theorem, the alternate angle is the angle made in the other sector from a chord. That's it for this theorem. This is one important theorem. Now let us see the next theorem on segments of a circle. That is going to talk about the angle in the same segment are equal. Let me draw a figure for this theorem. A circle with center O and it has a triangle. Let me draw one more angle here. Name the two angles A and B, and this is the segment. Let the angle AOC be X. From the previous theorem, the theorem we just discussed, we can say that X is equal to twice ABC. Am I right? This is what we just proved in theorem number 1. So replace AOC by X. If theorem 1 holds true, it will be true for the other triangle also. Am I right? ADC. So in the place of ABC, we can also use ADC. Let me name these two equations as 1 and 2. Please note that the left hand side of the two equation is same. So you can easily equate the RHS, that is the right hand side of the equations. Divide both the sides by 2. So you'll be getting angle ABC equal to ADC. It means angle in the same segment are equal, hence the theorem. These are the two important theorems on segment of a circle. We can use it in finding the area. Now we can see a set of solved examples and find the area of a segment of a circle. Area of the minor segment when angle and radius are given, and we can find the area of the major segment of a circle and area of a minor segment of a circle. A chord of a circle with radius and angle is given. We can use these three concepts and solve few examples. And we can also see the application of this theorem then and there in the steps of the examples. These are the types of the problem we are going to discuss in our next session. Area of a segment when r is given, when the angle is not given, when the chord length is given. Hope you are clear with the theorems we discussed in today's video. See you in the next video with the solved examples on these types. Have a great time ahead. See you in the next video.